Well, as we begin this chapter, we want to make sure that we understand what numbers qualify as perfect squares. All right? Perfect squares. And I guess if I was going to make a list of the perfect squares, I would make the list. It would go 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and it could keep on going. Why are these numbers right here, why are they considered perfect squares? Well, the reason they're considered perfect squares is because if I take 1 times 1, I get 1. And if I take 2 times 2, I get 4. And 3 times 3 gives me 9, and 4 times 4, and 5 times 5. And one way we could write that is 4 squared, and 5 squared, and 6 squared, and 7 squared, and so on squared. We're at 10 squared, and you probably have heard 11 squared is 121, and 12 squared is 144, and you probably need to start committing those to memory, those numbers that are perfect squares. Why do we care? Well, because in this chapter, we're going to take the square root of some numbers. We're going to say, hey, find the square root of 81. And we hope, if you know that 81 is a perfect square, then you know that the square rooting of that is 9. Square rooting is the inverse operation of squaring. When you square 9, you get 81. When you take the square root of 81, you go back to the 9. Squaring and square rooting are inverse operations. Okay? Be careful. You cannot take the square root of a negative number. All right? Don't do that. You could, however, do this problem, because this says just take the square root of 81 and then make the answer negative. And so we could say the answer to that is negative 9. But you would only be negative if there's a negative out there to begin with. All right? Also, we're talking about perfect cubes, all right? So what are the perfect cubes? Well, 1, because 1 cubed is 1. 8, because 2 cubed is 8. 27, because 3 cubed is 3 times 3, which is 9 times 3, which is 27. 4 cubed is 64. 5 cubed is 125. And really, those first 5 are probably the ones that you want to remember the most, all right? Why? Well, because you're going to be asked to take the cubed root of 27, and you need to know that it's 3. You're going to be asked to take the cubed root of 125, and you're going to need to know that it's 5. All right? Notice it's not square root anymore because of this 3 here. We refer to that as the index. That's what that's called. All right? This is called the radical sign, or the radical symbol. And whatever's underneath the radical sign is called the radicand. Okay, so there's some terminology, vocabulary for you. All right, so you're going to be able to need to work with perfect squares and perfect cubes. Okay, now where does that lead us to next? It leads us. It leads us to the idea of rational and irrational numbers. All right? Some of the numbers that we work with in math are considered rational. Some of the numbers we work with are considered irrational. All right? Now, I'm just going to tell you that most of the numbers we work with are rational. Okay? Because rational numbers include whole numbers. All right? We're used to working with whole numbers, right? Integers. What are integers? Well, integers are just the positive and negative whole numbers. If whole numbers are 0, 1, 2, 3, 4, and so on, then negative 3, negative 2, negative 1, 0, 1, 2, 3, those are the integers. Okay? And also, if you were to take the square root of 25, you get a whole number, right? Yep. Fractions and decimals can also be rational. All right? They can also be rational. So, in fact, here's the real definition of a rational number. A rational number is any number that can be expressed as a fraction A over B. All right? Well, wait a second. I thought we said whole numbers were rational. Well, they are, because 5, the whole number 5, can be expressed as a fraction, 5 over 1. All right? What about 10 over 2? Is that rational? Yeah, it is. Okay, because it's 5 over 1. Okay? What about 1/3? Isn't 1/3 0.33333 or 0.3 repeating? Yes, but because it can be expressed as a fraction, it's rational. In fact, any decimal that terminates, okay, or ends, that's what terminate means, or repeats forever, all right, in some form or pattern, if it's a decimal that terminates or repeats, it's a rational number, all right? So pretty much we've covered every number that we've ever looked at. So what numbers could possibly be irrational? Well, the irrational numbers pop up when we start to take the square root of numbers that aren't perfect squares. The square root of 26. Well, I know that the square root of 25 is 5, right? And so that means that the square root of 26 is probably 5.134767, and I'm just making up numbers because they're never going to stop, they're never going to end. This, my friends, is an irrational number. All right? If I try to take the cube root of 9, well, I know that the cube root of 8 is 2. So this must be 2.3147, blah, 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 forever on and ender, never repeating, never ending. That is irrational, all right? So where do our irrational numbers come from? Well, almost all of them come from trying to take the square root or the cube root or any other kind of root of a number that's not a perfect square or a perfect cube or a perfect whatever you're trying to take, all right? Good luck with rationals and irrational numbers.